Welcome to our lectures on the DC microgrid and control. So, we shall continue our discussion in power electronics converters, application of the power electronics converter in DC microgrid. So, today we will discuss about the pulse width, different kind of pulse width modulation technique that is useful, and it will be used in the DC to DC converter or DC to AC converter. And paralleling strategy first we will check for the half bridge converter, followed by 3-phase bridge converter with sinusoidal PWM, modulation technique for the multi-level converter that we require to understand. And nowadays you are simulating maybe the DC microgrid, and we require to understand that how you use the different kind of multi-level inverter and how you can fit it to this power electronics module to be integrated into the DC microgrid. And apart from that, modulation technique for the different kind of multi-level inverter. So, that is basically diode clamp and flying capacitor FC, and this one mostly will be discussed about the cascade H bridge CHB. So, these are the two changes you will make it, we will do it. Thereafter, we shall see that hysteresis modulation and PWM technique also for the not only AC to DC converter and DC to AC converter or rectifier inverter operation, also DC to DC operation. So, in order to improve the quality of the output voltage, PWM technique is used. What essentially PWM does, it shifts the harmonic to the higher frequency range for the voltage as well as the current. And then since our power system is essentially a low pass filter, so this high frequency voltages will be reduced with the effect of this low pass filtering effect, and thus you get the better TSD. So, PWM technique, the output of each converter pole is switched several times during the fundamental cycle between the positive and the negative terminal of the DC link voltage. So, it will switch over for the 2-level inverter, it will switch over to the plus PTC to the minus PTC. If it is a multi-level inverter, then different level it can be switched on. So, different kind of modulation technique required for multi-level inverter or 2-level inverter. The time interval between consecutive switching is controlled, so that the average of the positive and the negative voltage per second segment of the output voltage is matched, and thus you do not have any DC offset. Otherwise, if it is positive area and the negative area does not match, you will have a DC offset. Moreover, the volt area that you generate by the PWM should match your proper sine wave. So, the waveform follows this required sine wave. By increasing frequencies, harmonics in the lower order frequency range can be reduced. Essentially, it is transferred to the higher frequency range, and ultimately voltage harmonic remains same, but current harmonic is been reduced drastically with the effect of the filtering effect of the power system, or the size of the inductor or the filter becomes lower. So, how it will be done? It is done very simple way. You have a sine wave and you have a different kind of modulation technique which has been discussed in the different books also by NPTEL courses of the advanced power electronics, you can refer. So, this has to be compared with the triangle wave, and ultimately you generate a bidirectional pulses. You can have a unipolar pulses, you can have a bipolar pulses. This is a bipolar pulses, but we prefer to the unipolar pulses. A carrier signal with a sawtooth waveform can be compared with the sinusoidal wave to generate the pulse width modulated output voltage as shown in figure 1. The frequency reference of the frequency or the reference frequency RF must be equal to the desired frequency of the fundamental of the output voltage. In case of the line operation, you require a 50 hertz supply. The carrier signal repeats itself with a period Tp and the switching frequency Fp equal to 1 by Tp. So, you can have this as a reference and you are comparing with a simple comparator in an open loop. Thus, you are generating and ultimately if you ultimately inverter essentially amplify these voltages to the plus VDC and minus VDC, and when you filter it out then you get this kind of sinusoidal waveform. Now, consider a half bridge topology where voltage will be reduced here. Consider a half bridge converter shown in the figure controlled by PWM strategy. The DC-link voltage is denoted by VDC and the potential of the phase leg is denoted by VAT, whereas the voltage and is denoted by the VL. So, half bridge converter operate based on the alternate switching S1 and S4. The turn off or turn off commands of S1 and S4 are used through the PWM strategy. So, this is S1 and S4. The PWM strategy compares a high frequency periodic triangular carrier signal with a slow varying modulating signal, as this is around 20 times higher than the carrier signal, and if it is higher then it will be S1 will be on, and otherwise if you are not get then S4 will be on, very simple thing. The switch conducts only if the turn on command is provided to the current flow through the IGBT or the MOSFET from the collector to the emitter. The PWM process is illustrated in figure 2b, and whereas the switching function SW of the switch is denoted as 1 if switch is turned on and 0 if switch is turned off. So, this is a simple logic. So, PWM strategy for the control of the half bridge converter. The carrier signal has a periodic waveform with the period Tp and the swing between -1 and +1 as shown in figure 2c. The intersection, so this is the intersection, this part you can see that triangle is more than the carrier, and in this part totally the signal is more than the carrier. The intersection of the carrier and the modulating signal is determined in the switching instant S1 and S4. So, see that it is S1 and it was on till the carrier waveform is less than the signal. Once this happens, carrier waveform will be carrier waveform is more than the signal waveform, thus S1 will be switched off. And thus what happen, S4 will be turned on for the small duration of time. Similarly, for this duration again T1 will be turned on, and here for this small duration of the time this will be turned on. So, what you can get essentially a bipolar voltage. So, here you get plus VDC by 2, and for this reason you get minus VDC by 2 and so on, and since the average is positive. So, you will get, you try to encircle the sine wave. This is the operation of the half bridge. Similarly, the VSC and the grid are modeled as two 3-phase sources, and the grid line filter is placed between the two phases of the voltage. We will see it in figure number 3. The phase voltages and the current of the grid are denoted by EA, EB and EC, and currents as IIB and IC respectively. The resistance and the inductance of the filters are denoted by R and L respectively. The angular frequency and the phase to phase RMS voltage of the grid is denoted by the omega and E respectively. So, you can consider this is the simplified circuits for the grid connected voltage source converter, and B is essentially its DQ equivalent. So, what essentially you require to transform that ABC parameter to alpha beta to, this is called stationary reference frame of and it will have 2 axes, and when this DQ, when this alpha beta is rotated in a synchronous frame, then the quantities in 50 hertz become stationary. This is the advantage of it, and it is by the Clerk transformation, and ultimately you get the DQ. So, this is for the this is the 3 phase model, and this parameter essentially become DC here, and this is your ED and EQ. So, the instantaneous phase voltage of VSC is denoted by UA and UB and UC respectively. The phase voltage of the grid are given by, definitely it is EA under root of 3 by 2 E cos omega t. The relation between the current and the voltage of the VSC connect to the grid in the different phases can be written as it is. So, it is UA minus, that is a back EMF it is generating, it is thereafter minus IARA minus LDIDT equal to 0. Similarly, for the B as well as the C phase. In case of the 3 phase bridge converter, let us see with the sinusoidal PWM how does it work. The voltage source converter is connected to the grid with 3 watts and only Y point is grounded. Thus, no zero sequence current exists under this condition, and grid is represented by in a DQ frame as shown in the previous figure 3b, and this is the equation governing this equation. So, UA minus ED minus ID minus LDIDT equal to 0. So, you may confuse, I just told you that this parameter looks DC, then how this terms comes. So, you know actually it is reference frame itself is moving in a 50 hertz. So, thus this term will exist. So, similarly this is for the quadrature axis and this is for the direct axis. The circuits of the phase 3 phase bridge converter consisting of the 3 phase half bridge is shown in, will be shown in the next figure 4, and let us see that figure. So, this is VDC by 2 and this is VDC by 2, and it can handle the bidirectional power flow. This is essentially the EA, and from there is a source inductance, or you will put some amount of inductance to have a active filter operation, and so power can be flown this point to the DC and vice versa. If it is flown to AC to DC side, it is rectifications, and otherwise it is the inversion. The phase voltage and the potential of the floating stars loads are denoted by VA, VB, VC and UA, UB, UC and V0 respectively, that you can see what are the different parameter indicated. This is UA, it is VDC and all those things, and this point is the terminal voltage of the out. The valves of the or the switches, nowadays we do not use valves, of the VSC are controlled by the digital switching signal SWA and SWB and SWC respectively. If the SWA is equal to 1, then the phase voltage, then the phase potential and the phase leg actually it is VDC by 2, and if SWAT is equal to -1, then the phase potential of the phase leg A equal to minus VDC by 2. The reference voltage signal to the modulator consists of 3 phase voltages, which are can be described by UA, UB, UC, and have root 3 by 3 U cos omega t plus phi, root 3 by t u cos omega t plus phi minus 2 by 3 and 4 by 3 and so on. So, you can see the different kind of voltage. This is a 120 degree phase shifted 3 sinusoidal voltages. This is actually for the VAO and this is for the VBO, and ultimately if you subtract this and this, essentially you get the line current. Thus, negative term will cancel and you will have unipolar voltages in case of the line voltages. So, where U star and the omega are the reference value of the phase to phase RMS voltage and the reference angular frequency. The reference phase shift is denoted by phi. The carrier signal changes between plus VDC to minus VDC and is compared with the carrier 3 reference phase voltages, which forms a symmetrical 3 phase system. This voltage and the current on each phase are determined in terms of the switches in conduction at each time instant. Figure 5 will show little later that the carries shows the carrier and the 3 voltage reference of the sine wave for this PWM voltage source converter, and figure 5b shows that VAO and the AC terminal voltage with respect to the modulation index. So, this is the phase voltages and this is respect to this is the pole voltages rather, and this is the line voltage. Now, let us go into the multi-level modulation technique for the multi-level inverter. You have a different you have a more than 2 levels. So, multi-level inverter power electronics converter are developed to achieve higher rating suitable for high power application, whereas the number of power electronics devices are increased. That is one of the disadvantage you got, but power rating of these devices is lower. The multi-level converter are more flexible in operation because of the you can have a redundancy in the switching states. At the same time, with increased complexity of the modulation inlays algorithm required to be more complex one. Various modulating methods were developed to fit the converter topology, and a classification of the most common modulation methods of multi-level converter are shown in figure 6. The modulation algorithms are classified in terms of the average switching frequencies. So, this is the block diagram of it. So, we will show the different kind of switching strategies. So, you can have the multi-level modulation technique. One is if it is a low frequency, you are made by the GTOs or even SCS. So, you can use selective harmonic elimination and you can have a nearest vectors phenomena and also nearest level. From there, and you can have a high frequency switching pattern. One is hybrid modulation. So, that is basically you can use the SHE and both combined. Thereafter, you can have a multi carrier PWM. This is a phase shifted PWM, it is phase shifted by 60 degree or something, whatever the level. So, and you may have a level shifted PWM. So, the level shifted PWM one is actually phase disposition. So, this carrier are in a same phase, opposition disposition. So, these are anti-phase and alternate phase opposition disposition, all the permutation combination is possible and all has its own advantage and disadvantages even at a different kind of modulation index. And you may use space vector modulation, that is popularly used now. This is the 2D algorithm and this is the 3D algorithm. So, what happened here, based on this hexagon will increase based on the level, and we have a different switching pattern here. And of course, this hexagon can have many states. Space vector modulation has one of the advantage that it utilizes the better decelerating voltage, and for this reason and switching stress is less. Of course, same can be done by the third harmonic injection, but instead of doing that you can achieve that same features in case of the space vector modulation. Thus, PSPWM or phase shifted carrier PWM is a derivative of the traditional PWM technique adapted for the flying capacitor and cascade CHP application. Since each flying capacitor device is a 2-level converter and each CHP devices is a 3-level inverter, so the traditional bipolar and the unipolar PWM techniques are used. So, this is the catch here. And apart from that, this technique consists of introducing a phase shift between the carrier applied to the contiguous switching devices. Obtaining hereby a phase shifted switching pattern helps to reducing the harmonic level. The greatest reduction is achieved for the phase shift is 180 degree or 360 by n, where n is the number of level, number of switching devices. And phase shifted carrier pulse width modulation, this is a method based on the multiple shift between carrier and is an extension of the bipolar PWM to the multi-level converter. The carrier signal which is associated with the specific voltage is compared with the reference, and when reference is over one carrier, the corresponding voltage is generated. In a multi-level converter, M1 carrier signals are used for the M levels. The phase vector modulation or SVM is one of the most popular modulation approach for the 2-level converter and increasingly applied to the multi-level converter. It offers significant flexibility to optimize switching voltage, switching waveform, and it is well suited for the digital implementation because it is a 1 and 0 format. The control of the switching devices in space vector modulation strategy, this is the space vector modulation, is performed using the PWM technique, but the switching times and the switching sequence are determined based on the 3-phase vector representation of the 3-phase vector representation of the reference variables and the vector switching states. It has been discussed in the advanced power electronics courses. You can refer to the YouTube or you can refer to the books of Ben Hu and other. This thing has been covered in detail. Depending on the desired converter output voltage, reference voltage vectors are first generated, then mapped into alpha beta if it is a 3-dimensional space, alpha beta gamma state space, instead of using the ABC coordinate. Now, let us come to this is a very important topic, the space vector modulation. It is a different kind of algorithm. The number of states depend on the number of switching devices in the converter. The multi-level converters is possible to generate as many output levels of the voltage as many level in the converter has. Example of NPC which has 3 phases and 3 output levels or switching states are 2 to the power 3 equal to 17 possible combinations are achieved, of which only 19s are different and 8s are redundant. The SVM algorithms are classified into the 2 categories, namely balanced and unbalanced system. SVM for the multi-level balanced converter, that is for the balanced converter topologies, non-zero sequence, or you have if you have a 3-phase COS system with non-zero sequence component exits, thus you have another axis instead of the alpha beta. Thereby the reference vector is represented into the bidimensional state space. The closest three state space vectors to the reference vectors are combined in such a way that their time average equals to the reference vector. In power converter with neutral connection, usually called also unbalanced system, a zero sequence component appears, and therefore, the alpha beta lambda representation, which is the 3-dimensional representation, is used. Now, come about the hysteresis modulation technique. This is a nonlinear modulation. We shall discuss little later into the class. Hysteresis modulation technique is the simplest to implement and in practice. However, this has these shortcomings: variable switching frequency and hence spread harmonic spectrum, increasing current error if the middle point of the DC link and the system neutrals are not connected, and thereafter also poor quality of output current means it has to be used for other techniques such as repetitive feedback to improve the output current quality. And moreover, there is a designing challenge since it has a variable frequency operation. So, we require to put a inductor as we have seen in the rectifier, active rectifier. So, designing inductor is becoming challenging and other issues. So, now we will touch upon that PWM technique for the DC to DC converter. Now, we will have a DC, that is, let us consider that non isolated DC to DC converter. So, DC to DC converter, most popular PWM techniques also used. It is obtained by comparing the sawtooth waveform. There you had a triangular waveform, here you use a sawtooth waveform with control voltage signals as illustrated in the figure 7. So, this is the your sawtooth waveform and this is your maybe the capacitor output voltage, and it is swinging like this. Ultimately, what will happen? You can see that this is a duration and this duration changes, and you will have a different kind of switching pattern. Based on that, you will be switching on. Generally, what happened here? You can see that there is a error since we will compare it. So, here this much of error was more here, and thus you will have a different uptime. So, switch was maybe on here. Thereafter, you can see that this has been reduced. So, ultimately switch will be off for the more time. Again here error has been increased. So, you will change the duration of the switching. Another aspect is that the B type, you can also vary the carrier wave depending the error. So, it is called the variation of the carrier wave amplitude, that is also possible. Mostly we will use this pattern. This is a simplified version and easy to operate. The adjustment of the control voltage allows the adjustment of the output pulse width as shown in the figure 7a. As the control voltage is increased or decreased, the duty ratio is increased or decreased, causing an increase or decrease in the converter output voltage. For this reason, the voltage mode control is called duty cycle control, which largely employed in a DC to DC converter, but we will have a first current loop to compensate. We will see in details in the future courses. The pulse width control can also obtained by varying the carrier amplitude as shown in figure 7b. So, we shall carry our discussion with DC to DC converter in our next class also, and little bit of the control modulations. Thanks for your attention.